Bootstrap. We'll have Lorenzo Quintavalle telling us about Multipoint Conformal Bootstrap.
Thank you very much. And thank you very much for giving me this opportunity to present our work here at the Bootstrap conference. Today's talk is going to be focused on multipoint correlators, and in particular our studies on multipoint conformal blocks, what we learned from them, and their applications to the light control system. In particular, this talk is going to be divided into two parts. The first part presented by me, which is going to be mainly an introduction and a review on some of the results we obtained in a series of papers with Ilya Guric, Sylvain Lacroix, and Volker Schneiders. While the second part of the talk is going to be presented by Jeremy, and is going to focus on applications of what we learned in this series of papers, and in particular applications to the light control system. Great, but since this is a very perhaps unconventional setting for a Bootstrap talk, let me start by motivating why we want to study multipoint correlators. In fact, the usual Bootstrap logic only focuses on 4 points, since if one has full control over the whole set of 4-point functions of a CFT, one has enough information to get all the CFT data of a theory. However, we know that this is a very hard task. I mean, one needs infinitely many 4-point functions, and therefore we believe that studying multipoint correlators can be a shortcut to get more information, or perhaps more powerful constraints. So, in fact, it's very easy to imagine from the fact that a single multipoint correlator corresponds to infinitely many 4-point functions, that this can be indeed true. Not only that, but starting only from informations on external scalars, multipoint correlators give already access to spinning data inside, such as OP coefficients of multi-twist operators, more than one of them. Just to mention some extra applications of multipoint correlators, starting only from n equal to 6 onwards, one can take light cone limits of multipoint conformal correlators, and some nice relations between these light cone limits and null polygonal Wilson loop start to appear, at least in theories which enjoy dually conformal symmetry. And this has been explored already in some very nice papers in the last 2-3 years by this gentleman here. Last but not the least, as it has already been shown in a paper of last year by the Porto group here, it is possible to do light cone bootstrap and get some new results which were previously unknown just by working with multipoint correlators. And in particular, stay tuned for the second part of this talk, since this is precisely what we're going to discuss. Great. Now, let me gently introduce you to the topic by simply reminding you how correlation functions of more than one scalar look like. In fact, here we have, just as usual for the 4-point case, we have a multipoint correlator can be constrained by conformal word identities to acquire this form, namely a certain prefactor which encodes all the covariants of conformal correlators times a summation over products of OP coefficients and conformal blocks here. So these will be the protagonists of today's talk. And already by looking at the kinematics of multipoint configurations for conformal theories, it is possible to understand how this task, how studying these objects, becomes much more complicated very quickly. In fact, if we look at 5-point correlators, we have that the number of cross ratios is already 5, while for 6-point correlators, which is going to be the main focus of this talk, we have already 9 cross ratios. So you can imagine, since the number of degrees of freedom is very high, it gets very complicated very quickly. Okay, now, I told you the protagonists are these conformal blocks. These conformal blocks depend on 9 cross ratios for the case of 6 points, but then they also depend on a set of labels which also depend on the way we're working with the OP, with the operator product expansion. In fact, starting from 6 points, one has 2 different topologies for operator product expansions. This above is the so-called comb topology, while the one below is the so-called snowflake topology. It's hard to write here. And they will be the channels that we will focus on the second part of this talk. Now, just to introduce you to what's happening in here, we have in the COM channel, just a series of OPs, one after the other, successive OPs. Whenever we take an OP of two scalars, we produce symmetric traceless tensors characterized by conformal dimension and a spin. This spin corresponds to the length of the first row of a Yankee-Blow representation of this field. And whenever we take the OP of a symmetric traceless tensor with a scalar, we produce a mixed symmetry tensor, so we have access to a second row of the OP. So in particular, this kappa label that you see here is going to represent the length of the second row. But in order to fully specify a conformal block, we don't only need the quantum numbers of the exchange operators, we need a number of labels which is equal to the number of cross ratios, so 9. Here we have a total of 7. The two leftover degrees of freedom simply are associated with the vertices in here and encode the invariant tensor structures that sit at those vertices there. In fact, if you focus on this 3-point function here, you clearly see that this is a spinning 3-point function with two spinning fields, and it has therefore a leftover one-dimensional freedom from conformal symmetry. And this is parameterized by some integers. When we move to the snowflake channel, the situation is simpler in terms of fields that are exchanged. In fact, we have only symmetric traceless tensors, but at the vertex we have a bigger freedom in the 3-point function, since this involves 3 spinning fields and has therefore 3 associated integers. Great. Now, this is the main setting, the main objects that we will discuss. Now let me start by reviewing briefly some of the results that we obtained in the first series of papers. And in particular, the main result of the first 2 was that we found out that the problem of computing multipoint conformal blocks can be recast as an integrable problem. In fact, we found out that studying Godin models for the conformal algebra, it is possible to construct a number of commuting Hamiltonians which, when taking certain limits, reduce to a number of differential operators equal to the number of cross ratios, and therefore to the number of degrees of freedom of our system, and which therefore can characterize our system fully. We have a number of conserved charges which matches the number of degrees of freedom, 9 in the case of 6-point functions, and we can therefore aim to obtain the conformal blocks by solving these differential equations. We're not there yet. The differential equations are rather complicated. 2nd, 4th, and 6th order, for example, for the COM channel in general dimensions, but this is a rather solid setting to study limits for these correlators. Let me focus in particular on the COM channel from now on, and for the COM channel we can construct a series of differential operators. Just to give a rule of thumb, we have quadratic Casimirs for every delta that appears in there. We have quartic Casimirs for every j. We have 60 Casimirs or third order Pfaffians whenever there's a kappa. And finally, for every tensor structures, we can construct some commuting, what we call vertex differential operators, which correspond to specific choices of tensor structures of the vertices. Great. These are very useful to get certain, to study certain limits of correlators. However, in this talk, for the sake of simplicity, and since they're the simplest operators to study in any case, the simplest one that one works with, we'll focus only on quadratic Casimirs. Good. And for the COM channel, as I was mentioning, we have just 3 quadratic Casimirs, as you can see from the number of deltas. We have D1, 2, obtained by summing generators from 1 and 2, D1, 2, 3, and D5, 6. Just to show you the way they look like, D1, 2, 3 is, you can define it to be 1/4, the trace, roughly speaking, the square of the sum of generators. And why are we interested in these operators? These, when they act on the conformal blocks, they give birth to some eigenvalue equations, such as the following one, which indeed are the ones that can be used to obtain information on conformal blocks. Now, here I'm also introducing some extra notation, which I will quickly explain in a moment. H minus t plus 1 plus kappa plus h minus h bar minus 1 psi. So this is the Casimir equation for the middle length. Here I introduced two new labels, which are h, which is basically half the twist, with the addition of this kappa spin, and h bar, which is what we can call the anti-twist, perhaps. Like this. And these encode the leading behaviors when one takes the light cone OP for a symmetric twist sensor and a scalar in particular. Good. Now, this basically concludes the introduction of differential operators. If there are no questions, I can introduce further tools that we use to work with these differential operators. And in particular, what I would call our cross-ratio toolbox. In our last paper, in fact, we introduced two different sets of cross-ratios, which are useful for different reasons. The first one we dubbed polynomial cross-ratios. Which have the characteristic of making all coefficients of Casimir operators polynomials. So if you write down a Casimir operator, for example, D12, this will look like a summation over some indices of polynomials of all the cross ratios times derivatives on all the cross ratios. So all the coefficients are polynomials, and this peculiarity makes working with these operators rather simple. In fact, this is the simplest form that we could find to recast Casimir operators. And taking light cone limits, for example, as Jeremy will show, will be a rather simpler task. Good.
So can I ask a question?
Yes,
So,
of course.
and when you define these cross ratios, they are designed to expand in one channel, right?
They are designed to expand in one channel, precisely.
And then if you expand in another channel, the Casimirs will look very ugly in the other channel, or are they also nice?
They will look certainly uglier. They don't preserve the polynomiality condition, but in a way, the way we work is in every channel we're focusing on the polynomial cross ratios tailored to that channel, and then we cross the cross ratios. We do crossing, we change, we know the relation between cross ratios. It's not that complicated. So once we find the solutions that we're interested in, we just change variables.
And these polynomial cross ratios, you will use them both for the snowflake and for the COM?
These polynomial cross ratios that I'm discussing here are mainly focused for the COM channel, and since in the last paper we actually introduced them only for the COM channel, it is possible to introduce them also for the snowflake, but actually the computations that we will do on the snowflake are much simpler. We don't even need them. Mainly, yes, for the first cases at least, this will become a 4-point function. So it's not that complicated to work with. Good. If there are other questions, feel free. Otherwise, let me introduce you which type of polynomial cross ratios one can build. For 4 points, the usual U and V are polynomial cross ratios. In fact, the usual U and V that one can build in this form, I like to use this way of representing them. I think I took it from one of your papers, where we're representing, each line represents a difference of positions squared, and intersecting lines represent those that appear in the denominator. So this is the usual U cross ratios, this is the usual V cross ratio, and for 4 points, these cross ratios already satisfy the polynomiality conditions that we will discuss. When one goes to higher points, one can certainly construct this type of cross ratios. One can repeat the same construction for all neighboring groups of 4 points here. So for example, in the COM channel, we have here 3 sets of polynomial cross ratios for 4 points, but then we need to introduce extra types that involve groups of 5 points. For example, U15, what we call U15 can be built out of 5 points in this way, maybe I should put also the labels, while U16, which is going to be a cross ratio involving 6 points instead, can be constructed this way. Great. So working with these cross ratios will make our task of working with differential operators much simpler, at least in the light limits. Another set of cross ratios that we introduced, furthermore, to work with OPE limits instead, is what we call indeed the OPE cross ratios, which have a number of interesting properties, in fact. They have a very nice geometrical interpretation. In fact, we can construct they are very natural in some conformal frames. They allow for a simple dimensional reduction of conformal blocks. So these are the way to go if one needs to go for higher points and reducing number of dimensions, since the gram determinant becomes very simple in terms of these cross ratios. But the main feature that we will be interested in, and the reason why they're called OPE cross ratios, is because they're rather natural in terms of OPE limits for correlations. In fact, if we draw a 6-point com channel diagram, for example, and let me add lines to remind you which fields are spinning, with how many spins, we can take a limit on 3 of these cross ratios, which is called Z2, Z bar 2, which are just generalizations of the Dolan-Walton type of coordinates, and a certain upsilon cross ratio. If we send all 3 of them to 0, we can basically cut this diagram along this middle line. So this is a rather unconventional OPE limit, but this allows to project on exchanges of certain mixed symmetry tensors in the middle, for example. And the end result is, in fact, a product of a 4-point function, or 4-point blocks, I should say rather, times some leading behavior in Z2 to the H, the twist, Z bar 2 to the anti-twist, and upsilon to the kappa. This times the 4-point function on the right hand side. And to remind you again about the spin flowing there, let me add you some extra lines here. So this is also a way to obtain differential equations for 4-point blocks which involve spinning external operators. We can just construct them out of multipoint correlators and cut the diagrams to reduce them to spinning fields, to external spinning fields. But
sorry,
yes.
I was a bit late. Kappa is the number of boxes in the second row? Or?
Precisely. Yes. And then I introduced the only 3 cross ratios, but other 4 of them are easy to imagine. Here we have 4-point functions, so we're going to have a Z1 and Z bar 1. Here we're going to have a Z3, Z bar 3. And of course, these are naturally embedded in the 6-point function. Plus, we have 2 cross ratios left over, and these are associated with the vertices here. These, again, are non-trivial vertices. They involve 2 spinning fields, and therefore have one degree of freedom left over, which is parametrized, which we parameterize at least, by taking an extra cross ratio and considering different powers of that. This is perhaps an unconventional way to work with 4-point functions, but it's rather natural from a multipoint case, since it's directly obtained from reduction of multipoint correlators. To perhaps connect this a bit more with what one normally does, if we cut again this diagram by taking an extra OP limit on Z1 and Z bar 1, what we're going to produce there is a 3-point function that involves 2 spinning fields. As you all know, this has a one-dimensional degree of freedom. We can parameterize this degree of freedom as powers of the tensors H12, what we also introduced V1, V2 to make the homogeneities of this object 0. This object to the n, this corresponds precisely to the x1 to the n, for example. So these objects, the tensor structures, are naturally encoded in these cross ratios that we can build for a 6-point function there. So it's a rather natural way to work with, to encode the various individual degrees of freedom of a multipoint conformal block in and associate them to each individual cross ratios. Great. And as a final comment on this part, let me mention what is the physical interpretation of this limit, since this is rather unconventional. In fact, I don't think it's ever been done at that type of OB limit of this sort. What this means, what we're doing actually in physical space, is we're taking two triplets of points and taking them to be infinitely separated, one from each other. So it's basically the usual limit that one would take to argue cluster decomposition of a certain correlator. Here, we're not seeing cluster decomposition since we're focusing on a conformal block. However, if we focus on a correlator, what we have, for example, 1, 2, 3, 4, 5, 6, what we have there is if the OP coefficient for the first three fields on the left, so let's say lambda 1, 2, 3, is not 0, we obtain usual cluster decomposition. Since in practice we are projecting on the fields which have the lowest exponents here when taking this limit, so the lowest one will usually be the identity. But if we cannot produce the identity in the middle there, in the middle channel, lambda 1, 2, 3 is equal to 0, then what we produce is basically a product of two 4-point functions, O, 4, 5, 6, divided by the 2-point function of O's. And this is somehow a first correction to the cluster decomposition, if you may, in the case in which the 2-point functions will vanish, the 3-point functions will vanish while taking them to be infinitely far apart. Great. Finally, okay, to connect to the next part of the talk, if there are no questions, the reason why we will need this thing, these OP limits for light-cone conformal blocks, is because this can provide boundary conditions for the differential operators that we will work with. In fact, I mean, you all know that when working with differential operators, differential equations, boundary conditions are almost as important as having the equations themselves. Without them, one cannot solve them. And these will be in particular relevant also for the light-cone limit to obtain normalizations. So now, if there are questions, feel free to ask them. Otherwise, I would welcome Jeremy to talk about the light-cone part. The light-cone. Yes.
So, can you provide some kind of physical intuition for why this integral quantum mechanics arise in the study of the whole? Is it just for kinematic reason, or is there some other physical picture?
I would argue it's just for kinematics reason. I mean, there is no. I mean, the CFT physics does not appear there. We're just talking about conformal blocks, so it cannot be. It cannot have anything to do with physics.
But suppose I look at dimension equal to 2 and look at large inner circle limit, where the blocks become classical. If there's some relation between this intuible model and the intuible models that arise in the study of four-dimensional gauge theories.
I mean, so I'm not sure I fully get the question, but what I can tell you is, well, these the differential operators that one can construct for these objects are in a way naturally encoded in some quantum mechanical systems.
Yeah,
with multiparticles.
Yeah, my question is where this quantum mechanical system comes from. If there's a physical origin, like whether coming from field theory or from string theory or whatever.
Oh, I don't know. It doesn't feel to. In a way, I think it's some kind of representation theoretic
that's what
argument, just not for coming from physics.
Okay.
Are there any more questions?
These conservations are written in your paper. I did not know about this upsilon.
Yes, they're written in our paper. In particular, we can define two different upsilons in a way. What we wrote in a paper is perhaps less useful in terms of computations, just restating of that conception, that epsilon. what one can work with. If you just remove everything that appears with square roots in the definition of upsilon, that's easier to work with and more or less has the same properties that you write. It just has a worse gram determinant, in a sense. But yes, they're in the last paper that you wrote, part 3.
Let me ask another question. So, when we work with 4-point functions, one of the advantages of this z and z bar, if I do computation in perturbation theory, they are full of square roots, and then I go to z and z bar, and they all disappear and so on. Do some of these cross ratios do the job of removing all the square roots also in weak coupling perturbative computation at 5 and 6 points?
Now, that is a very good question. It's, I think the reason why these computations eliminate square roots has to do with the gram determinant of 4 points. Because the gram determinant of 4 points is a mess in general cross ratios. If one works with u and v, it's rather complicated. If one writes it in terms of z and z bar, the gram determinant is something like z minus z bar squared of this sort. So, since the gram determinant is a perfect square, I remember certainly seeing in some integrals, conformal integrals, the appearance of this factor, the square root of this factor in particular, which drops out the square and therefore makes some computations rather simpler. Now, starting from 5 points onwards, I think this is not fully possible. In the sense, the nice gram determinants that we get are of the form, yes, z1 minus z bar 1 squared times z2 minus z bar 2 squared, z3 minus z bar 3 squared. That part can still be removed from the square root, but there is some leftover part which has to do with these x's and the upsilon in particular, which will not be perfect squares, so will still remain in the square root. And in fact, for example, one part that would appear in the square root, that appears in the gram determinant is x minus 1 times x, for example. If we take the square root of this, this does not simplify the computations. At least, well, it simplifies it partially because of the nice properties of this, but not the part in x. But still, I would argue, if one encounters a gram determinant in the computations, these cross ratios are really good. It's possible also to construct analogous cross ratios tailored to the snowflake channel. These are not present in our paper, and these will have, again, similar properties, similar behavior in the z's and z bars, and will have just an extension of this behavior of the gram determinant.
But then can't I just call x minus 1 y squared?
Yes, you can, definitely, sure. It depends whether it's natural in what one is doing, but it's certainly not so natural here in what we're doing in OP channels, but definitely one can do that. And perhaps, yes, it's already a great simplification, since if one were to compute the 6-point gram determinant, it would be a gigantic mess. While working with this, it's a very simple one-line product, or perhaps with something in the determinant. No, one-line product of cross ratios, and this part can be simplified just by simplifying it. So perhaps this can be useful in those computations as well.
Just so I understand. So, and would that work for one diagram or for the symmetric sum of diagrams in all channels? Or what you are discussing is for one particular contribution in one particular channel, which corresponds to this OP channel?
No, so if I'm talking about the gram determinant, I'm just talking about 6-point configurations. So it doesn't have to do with the channels. So indeed one can work with these cross ratios for general purposes. It's just when we wrote them, it was kind of trying to match the various needs that one can have, working with the various channels, like the OP channels, there, getting a nice gram determinants, and getting like good dimensional reduction related to that, and good geometrical interpretation in conformal frames. Yes. Thank you. Are there any more questions? If not, I will welcome you.
Right, so now I'm going to use this machinery that Lorenzo discussed for applications to higher point like on Bootstrap. In particular, the concrete goal you should have in mind will be crossing the snowflake into the comb. So let me write that down. Location. Points. Right. So once again, the goal will be the following. We'll want to do light cone bootstrap for this crossing symmetry equation, and in particular to compute and constrain CFT data of double twist and triple twist operators, typically at large tensor structures and large MST spin kappa. At least one of these will be large typically. And long term, this was the beginning of a more systematic approach to computing this kind of data, and maybe even in the further long term, studying things like analyticity and spins for these higher twist families. But yes, this is the focus for this talk. Before I get to this, let me provide an illustrated example from 4 points. So just the most basic exercise one can do. Look cross S to T. And we find that the identity of leading order is given by a large spin sum of double twist operators in the cross channel. So as usual, we'll take some light cone limits. As follows, we make 1 and 2 light separated first, then 1 and 4 light separated. And for this example, I'm working in the polynomial cross ratios of the 4-point function, u and v variables. And just remember that u scales with x12 and v scales with x14. And crossing symmetry equation in this limit. So essentially the direct channel is very simple to write at leading order because we know that this limit goes to leading twist, as Lorenzo reviewed, and the lowest twist operator is the identity. So in the left-hand side of the crossing equation, I get some power law at leading order times 1 plus higher twist contributions from the leading twist operator O. And this will be equal to sum of blocks in the cross channel with product of OPE coefficients, which I generically call the O. This depends on 2 cross ratios. So this is the object of study, and as you know, we can do Bootstrap with this. So the way I'm going to simplify the right-hand side is by looking at cross-channel blocks, but studying them via the Casimir operator, via differential operators. And so I'm going to want to get this result specifically just using differential operators. So this is perhaps a lesser known fact that one doesn't need to know very complicated integral formulas about the light cone over T and so on. One can just use these operators. So let me look at cross-channel blocks. I'm going to take the light cone limits in my Casimir operator. To do this, I'm going to introduce some bookkeeping parameters epsilon. So epsilon 1, 2 denotes the small distance between, light distance between x1 and x2, and epsilon 1, 4 likewise. And then at the end of the day, I find a very simple formula for the Casimir of the cross channel for 1, 4. And this goes at leading order in this limit, like 1 over epsilon 1, 2 du u du plus order epsilon to the 0 terms. Okay? And so what I want to explain now is that just using this form of the differential operators and our OP limit boundary conditions, we can very quickly, very easily derive the leading OP coefficients in the cross channel. And I'm going to do this in a three-step process, which will also carry directly to higher point cases. This is why I'm introducing it. So step 0 is essentially identifying the twist in the cross channel by matching the x14 asymptotics in the cross channel. So essentially I take my b to the twist over 2 times the function of u at leading order. And because of the limits, I know that this exponent encodes the twist in the cross channel. Step 1 will be identifying the dominant regime over which the sum over spins in the cross channel must be done to reproduce the direct channel. And the well-known result that it corresponds to j squared, scaling like 1 over x12. And I'll rederive this simple way. And then the last step involves simply finding the right formula, an analytically controllable formula for the blocks in this regime. And I'll do this by solving the Casimir equation, which, as you can see, is a much simpler equation than the most general one. And using the OP limit as my boundary condition. Okay, so this is my three-step process. Let me also comment while I'm here that it's very nice to take these limits in polynomial cross ratios because you can do the exercise that if you have a differential operator that scales with a negative power in this limit, and you know that you have a differential operator with polynomial coefficients, this is very constraining, and there's not many more possibilities for how the operator can look like at leading order besides this very simple kind of factorized form with a derivative on the left. So this is what allows us to continue to get simple formulas at higher points. Okay, so this is the three-step process. I'll now derive it using this differential operator. If you have any questions along the way, please feel free to ask.
Yeah, before you continue, and I forget it.
Yes.
So in the beginning, you said you're going to take a large also tensor structure limit today.
Later on, yeah.
What does it mean to consider, okay, the case spin I can sort of imagine, but what does it mean to consider an operator as large tensor structure?
Well, it means, sorry, yeah, that's a good point. It's the 3-point functions that have large tensor structures. So,
Okay.
this diagram will contain a 3-point function, as Lorenzo showed. So in other words, your blocks will be proportional to OPE coefficients of a spinning operator O1, phi, and O2. Actually, here it's 2, 3. And this 3-point function will not be fixed by conformal symmetry. There will be a finite number, there will be a finite dimensional space that it lives in. In this case, it will be n equals 0, 1, all the way to the minimum of j2, j3 minus kappa. So taking large tensor structure, well, first of all, it requires taking both spins to be large. And then one can focus on this particular component of the 3-point function, which is n going to infinity. This is what we do. Maybe I should stress that you don't have to do this, and we'll be able to construct cases where we don't do this. Actually, this will be one of the examples I look at. But for example, in 5 points, this is what you're forced to do when you want to match, for example, an identity contribution in the direction.
So to phrase it another way, will in the end the CFT data depend on this n parameter in general?
Yes, absolutely.
Okay.
Yeah. It's a labeling of CFT data. So you're just lucky that when you look at 2 scalars into an STT, there's only one single tensor structure. Otherwise, there will be a number of them for at least 2 STTs being exchanged.
So it's large number of tensor structures, the length.
Well, it's more like you're singling out one of these guys.
And yet the largest.
Yeah. So I can be more specific that it singles out the contribution where you take a 2-point function, for example, in this case, this tensor structure that appears in the 2-point function. So you take the term that has the highest power of the 2-point tensor structure. Okay, but I should stress that there's no tensor structures in the 4-point case, of course. We just explain. Okay, so yeah. So let me go quickly through the 3-step process. Step 0, it simply follows from the fact that the operator that diagonalizes a power law in V, it will commute with the Casimir at leading order. So this means that I can impose this power law asymptotics on every single block at the same time. Right? So I can impose psi O going like V to 2H5 times a function of U in every block. Okay, and this tells me that I'll have to sum over a family of operators with twist 2H5, twist over 2, 2H5, and this is known as double twist. Step 1, we can do a simple argument. People talk about the left-hand side being Casimir singular in the cross channel, and the argument is quite simple. I look at the left-hand side of my crossing equation. I act with this operator, and I see that this 1 over epsilon term does not kill the left-hand side. It keeps it, so the action of D14 on the left-hand side scales like this. But then I do the same thing on my right-hand side. I'll see that D14 acting on my sum over double twist operators is also of this order. Right? So, since this is diagonalized in every block, this tells me that the leading contribution is a sum over blocks with spin order 1 over epsilon, as advertised. Okay, so we're almost there. Now we know what region to sum over. And now we just have to solve this pretty simple differential equation to get the leading behavior of blocks. So I'm going to need more space. If it's okay, I'll erase. So I just need to solve du times this function, which is the block divided by the twist. Equals j squared j of u. At leading order, okay, this is the Bessel equation after a change of variables. So I get j normalization times k0 of 2j squared root 2. Okay, the last step is the normalization, and as I said, we get it from the OP limit boundary condition. So how do we fix the normalization? Essentially, we start from our block, and we know that it has to agree with 2 limits. So one limit is what I computed here, uv goes to 0, and the other limit is v1 minus u goes to 0. So let me just write this as the OPE limit. And we know that we get asymptotics as 1 minus u to the j, v to the h. So in practice, to do this with higher points, we'll start with the formula in OPE cross ratios, and then translate back to polynomials. Okay, so this is how I fix the normalization, and now I have everything I need to compute this leading term. So the end result of my 3-step process.
So the normalization is fixed by the symptotic, large argument asymptotics of the Bessel function. Yeah? That's the OP.
You can, no, it's a different limit. So really, I can go into it in more detail, but so you get OPE is U goes to 1, whereas the Bessel or the light cone limits is U going to 0, right? So I'm going to need to connect my block between these two limits. In practice, the way one needs to do this is to solve for all v this equation. So I need to pick up the corrections in epsilon 1, 2. I'll get the light cone block, so I'll get a 2f1.
But I thought you wanted you were trying to show an alternative derivation without going through the 12-1.
So let me put it this way, it's still, I didn't want to write down the full differential operator for all orders in U, but I could have done that. I would have solved this differential equation. We can also do the equivalent at higher points, also without using any integral formulas. And then I just normalize this solution to all orders in U, and I obtain this formula. So unfortunately, it takes a while to explain this for higher points, but you'll have to believe me that we can essentially take d1 squared, take the 1 over epsilon term, plus the epsilon 2 0 term, plus the epsilon 2 1 term. So at all orders in x1, 2, we just get a hypergeometric differential equation, which is solved by this, and then we connect the two limits to get the normalization. And for 5 points, it's quite straightforward to cook up a similar setup. It's essentially based on taking appropriate limits where the higher point function, higher point blocks factorize into products of two f1s. And this is in a sense corresponds to taking limits of lower dimensional kinematics. So I can go into this in more detail after the derivation for higher points, but yeah, this is what's unfortunately too short to explain in half an hour, but please look it up paper when it comes out. But yes, so if there are more questions, please ask. Otherwise, I'll close this part by saying that at the end of the two-step process, where you get this Bessel formula for GJ, we can solve for the OP coefficients, and we just get d over u to h5 plus corrections is integral dj in the region goes like 1 over epsilon phi phi j nj d to 2h5 k0. And plugging in a simple power law ansatz as usual reproduces the leading order asymptotics of the OP coefficients. Okay. So now I want to repeat this three-step process in a 6-point case. Before I do that, let me mention that we can do the same thing in 5 points and retrieve the results that the people here in Porto have derived with very different methods. So I can take this kind of crossing equation that preserves cyclic symmetry, so a planar crossing symmetry equation. I start by taking a light cone limit in x1, 5 with the identity here. That forces phi exchange here, assuming C phi 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 is non-zero. This is non-trivial, and then I'll do step 0. I'll see that I'm forced to have phi phi exchange on both legs. I do step 1 by getting computing the differential operator at this leading order. I'll see that I'll need the following asymptotics. So this time the spins will scale with 2 limits. And finally, I'll solve the blocks. This time my cross channel is 1, 2, and 4, 5 OPEs. Like this. And I have to add the dependence on tensor structures with the OP limit as a boundary condition. And I'll find that this boundary condition forces my tensor structure to also scale with the 1, 5 limit. Okay? So I can do this in a completely analogous way to what I showed for the 4-point Light-Cone Bootstrap. And at the end I'll deduce the OP coefficients derived by Antonio et al. About a year ago, I believe. Okay. I could also go at further subleading orders in the direct channel and bootstrap those. I'll retrieve, for example, anomalous dimension corrections from the 4-point function, also subleading OP coefficients. But if you'll allow me the time, I'd like to look at the first non-trivial example of the goal I wrote at the beginning to show what we can do with our machinery that would be particularly difficult to do with more traditional methods. Okay.
But I did not get yet to what was the main new thing. So because in the previous case, in the end, you still needed to use this 2f1, so you still need to solve the full Light-Cone differential equation. And here you say that if you do it, it's still just some simple hypergeometric. So the block, the 5-point block in this Light-Cone limit is just some simple hypergeometrics.
So I'll have to, I won't be able to, no, it's not. So I'll only be able to use, so the point is to get the normalization, I won't need the full Light-Cone block in the 5-point case. I'll just need to, because I'll have one extra degree of freedom corresponding to the tensor structure, and I can play with it to interpolate different regimes. And that's what I'll use to fix the OP limits. Essentially, so I'll have my U5 here. Let me also mention that in the derivation, in the previous derivation, there was no need at any point to swap limits in U and V. And so it was very straightforward, just taking the same limit on both sides, just with different Casimir operators that have a different eigenbase to the blocks, and that makes the derivation, for me, conceptually more straightforward with less things to prove. But
So
in the 5-point case,
when you write step 0, you are kind of assuming that you can stop the limits, right? Otherwise you have to, like in 4 points they have shown that the corrections to that behavior are really suppressed by spin or by z going to 0. But when you write that v goes to the twist over 2, you are saying something about the theory or not?
like no, I'm just taking the x14 much less than 1 limit after taking the x12, and then I find in my sum that higher twist blocks are suppressed. But I have already taken that, so I guess I go like this. I go 1 over epsilon 1, 2. I get this du du, and then I get an order epsilon 1, 4 correction, which I also neglect.
Okay.
So that's why I can confidently say this. Right. Okay, so the time is limited. Should I discuss the decoupling, or should I do the?
By the way, your thoughts are very pedagogical. I would say we have no second thought, so we could relax and go to break and continue a little bit afterwards. So don't.
Yeah, that's fine. That's fine.
So don't worry.
Yeah. Okay, good.
So, but let me understand. So, if you were to solve this, the blocks are the same blocks that we wrote and that Antonio and friends wrote, right? It's the same block. Or it's already defined.
No, it's so you guys, the blocks you have are in a swapped order of limits. So you have the equivalent of taking in the 4 points v less than u less than 1. Of course, in 4 points you can swap the limits, but here we have an extra player in the game which is this U5. So in other words, we have 3 limits. After fixing the twist, we have 3 limits in the game, right? And so here's how I can explain it. The blocks that you guys get in the cross channel, you guys take this limit and this limit, but in your blocks, you keep this finite, this x15. Then you have to do finite sums, and then you'll get these gammas of n's, and then you take n to infinity. Whereas what we can do with differential operators, and this is actually, once you know the details, very severe simplification, which is very useful, is that if you take this limit first, you can immediately take, this corresponds to immediately taking n goes to infinity, and your Bessels collapse into exponentials times power laws. So instead of having to resum these Bessel functions, and then take a Stirling formula in gamma functions, you can immediately get large n blocks from this first limit corresponding to this. And then you have very simple forms, blocks to integrate. So this is the main difference, and this is the main advantage of differential operators, and this will continue to carry through in this example where instead of just taking these guys first and only doing this at the very end at the level of OP coefficients, we're going to take this guy first. And this will lead to very strong simplifications of the blocks that we can really play with. So maybe I can go over in the time that remains this argument of how to get the blocks from the normalization, or we take a break.
So we are 1 hour now. So well, depends on you. How much time do you need for this part?
This takes 10 to 15 minutes, and this also takes 10 to 15 minutes.
I think given that we are giving you a second half, let's take a break at regular time. Let's do it more relaxed all together more.
Let's get this first part.
Okay, so let me start by, for the experts in the audience, quickly giving an idea of our approach to bootstrapping these OP coefficients in the 5-point function. So as I said, we can continue to follow the 3-step process. I hope this is clear enough. The order of limits is, as usual, we want x15 first to project a leading twist identity exchange here. Then we take the second Lightcone limit of the direct channel, and then we move on to make all neighboring points that remain light-like separated, and this in particular will project a leading twist in cross channel. So once again, for non-experts, no need to stare at these formulas too long, but I just want to emphasize that we get, once again, very nice simplifications at leading order for our differential operators, which allow for explicit solutions. And the slogan is that connecting these solutions to the OP limit, which acts as our boundary condition for our differential equations, gives us the right normalization to explicitly solve the OP coefficients. So this is a quick aside for how does one get the normalization. One has to, so the crux of the argument is playing with the 5th degree of freedom in the 5-point function coming from tensor structure. So here's the idea. We start, we know what our twist is now. So we take these limits and we obtain Lightcone blocks. And essentially we know that if we take the same limits as I described here, we'll obtain the same leading term and the same functional formula. So these differential operators They give us almost exactly the form of the blocks except for this number. And to get this number, we essentially combine several limits. We essentially need to connect this solution to the OP limit where we know the exact leading term, up to including the multiplicative constant, which is 1. So we start here for any x15 and any x23, x34. We use this nice result we found with differential operators that when we take our OP cross ratios to 0, we can factorize our blocks into a product of two hypergeometrics. You can understand this as a form of two-dimensional kinematics where you're making chiral exchange in one leg dominate and anti-chiral in the other. But so we get this product of two F1s, and we can connect this smoothly to the OP limit to get a normalization here. So now the job is to connect this 2F1 to our solution here. And we can do that by taking these like distances to 0 and getting the formula derived by Guerra et al., which, once again, we also find up to normalization from differential operators as some power laws times products of Bessel functions. Now, we can continue to take the x goes to 0 limits of this Bessel function, and here we can take the epsilon goes to 0 limits of our two F1s, and we allow ourselves to connect these two solutions and retrieve the exact normalization here. The final step, and I understand this is quite complicated, this was obtained for any epsilon 1,5, so we can take this solution. I don't have enough arrows and directions on the plane to describe another direction, but this last direction would be taking epsilon 1,5 to 0, and we obtain the leading contribution in 2. So this will be in our paper, of course, and it's a lot of limits to understand, but the point is simple. We find simple ways to connect the OP limit boundary condition to our limits, and this fixes the normalization.
And can you remind me, when we did a bootstrap for 5 points, we did not use this such a simple form, or did we?
You use this.
But you say that we could have used just that and it would be the
Yes,
same.
exactly. You could have used this, and it would have been much simpler. So, in other words, you guys have to integrate Bessel functions with n. And that'll give you, in your OP coefficients, 1 over gamma n plus finite. And then you'll have to use the Stirling formula, and you'll get n to the minus n and so on. So we kind of, we can go past that by directly taking a Bessel formula, a Stirling formula in Bessel functions, by imposing this following scaling in n. This is how it goes. And one can do that immediately in the books. That's the point. If one takes the right order of limit first, so one starts with the light cone limits that impose leading twist in a direct channel, as one should always do. Okay, so if there are no more questions, I'll move on to sort of the most novel application of this machinery, which is bootstrapping one leading contribution in this crossing symmetry equation.
Oh, sorry. Is it clear whether this diagram is commutative or not?
I believe so. I don't have a simple proof right now off the bat, but I'd be happy to discuss it, and I'm quite confident it is. So in other words, yes, we can, that's the whole point of the derivation. We claim that we can go to the same place with two different paths. And that's how we get normalizations. Okay, so without further ado, I'll get to my goal. now let's be a bit more specific. N equals 6. Crossing. Like this. And the specific term I want to bootstrap is starting with the Litecoin limit in 1/6, identity is the leading term, then a subleading contribution in O. And I want to explain how this gives us, at leading order, these OP coefficients, where O is the leading twist operator in the phi OPE, and this will lead to a phi O double twist exchange in the middle leg. And I'll be, for simplicity, in this example, looking at the case at a specific tensor structure, because that simplifies the calculations, although nothing stops you from looking at a more general data, more general kinematics.
Is it not so natural in this case to recover what we already got from the 5-point function, meaning the large n limit there? It's harder than just having n equals 0 in this calculation?
So the full result is a triple scaling limit. So you're going to have n1, n2 kappa going to infinity at the same rate at leading order. So they have
how is there a kappa there? That's phi what?
That's phi O, where O is.
Okay.
So indeed, that's a very important point. Assume O is an STT for this derivation.
Okay.
That'll be important for these limited tensor structures I'm considering. You don't have to in general, but this is what I'll be considering. Okay, so first of all, as I said, we want to project a leading twist here, we take x16. Then we want to project a leading twist in the two other snowflake OPEs, so we take this. And then finally, we're going to want to project a leading twist here. It'll also be useful to take these limits for a large spin, so all other neighboring points become lightly separated. And then final thing, so this is a consequence of what Lorenzo showed in his results on OPE cross ratios, but leading twist in the middle leg can only be so we can only suppress higher twists in the middle leg by taking this extra limit. So this is one of the three limits known as the origin limit in the snowflake bootstrap, but we only take one. So crossing symmetry equation, I can write the direct channel without too much difficulty. As usual, I have this leading power law in polynomial cross ratios. I'll have the contribution of three identities, but I'm not interested in this. I can bootstrap it, but it won't be very interesting OPE coefficients because it forces phi exchange at the middle leg. So I'm going to consider the next order, and that corresponds to, as I said, the two O's. I'll get a light cone block in this 4-point function with U2, V2 cross ratios. I'm going to expand it in the light cone limits. V2 goes like x3, 4, so I'll get this log divergence at leading order with the numerical coefficient that I know from 4-point blocks, and then order 1 corrections. And then finally, any higher order correction in the direct, or any other contribution in the direct channel will be suppressed by the twist in the 1/6 OPE. So this is my direct channel, and as usual, I want to equate this to a sum over cross channel, this time cone blocks. Okay. So let me quickly rewrite the three-step process because I want to push the idea that this is quite a universal approach. So once again, we'll identify psi O in the cross channel. And these last leg cone limits will be forced to take u to the twist asymptotics, and that'll fix the asymptotics, the twist in each leg. Step 1, we're going to act with our leading Casimir, the leading divergence in our Casimir on our left-hand side. This will tell us about the regime of spins we have to sum over. We're going to get, it's going to tell us which regime of spins in the cross-channel sum dominates in these limits. And then finally, 2, we're going to solve the Casimir equations in this regime using the OP limits derived by Lorenzo's OPE cross ratios as a boundary condition. So this is the three-step process, and I'll do this in more detail now. But if you have any questions along the way, please ask.
So just to understand, is it straightforward with this to get the OP coefficients for the double traces with Laplacians? The ones with dimension with twist to delta phi plus 2n.
It's a straightforward perturbation theory. We haven't looked at it yet, so I can't say anything conclusive. But once again, it'll be higher order corrections in this last limit in one of these guys. So for example, 1 and 2. These typically appear at order as order 1 corrections in your Casimirs. You can correct that in the blocks, correct that in your crossing symmetry equation.
Sorry. Isn't it related to the left-hand side when you get also the powers of descendants of the leading twist?
Absolutely, yes. So that's what
then
I'm
it's
saying.
related to x 2, 3 and x 4, 5. No? Is that where you pointed to? Sorry, maybe that's where you pointed.
I guess.
I thought you pointed to x1, 2, but you should be pointing to x 2, 3.
No, okay, sorry. So you're talking about corrections from descendants.
Right, because corrections from descendants there typically are mapped to subleading twists on the cross channel.
Yeah, no, but so that fits, because these corrections that you're talking about in this setup are controlled by U2.
Yeah.
And U2 is precisely the cross ratio that controls this twist in the twist in the middle leg. So this will lead to corrections at higher end in the middle leg.
Okay.
So I'm quite confident this can be worked through systematically. It's just so much to do, we haven't gotten to it yet. So, right. So let me start by simplifying the kinematics here as I said. So first let me make the comment that despite all the limits we've taken, there's still degrees of freedom left. So the number of cross ratios in this setup that remain is 9 minus the 7 light cone limits we took is 2. And these degrees of freedom, my claim is that they'll correspond to the tensor structures of the OPE coefficients of operators propagating in the middle legs. So to simplify this for this pedagogical example, I want to set x1, x2 equals to 0 in the crossing symmetry equation. I can do this on both sides because it doesn't change the behavior in the direct channel. So this will imply by comparing the OP limit that Lorenzo wrote down, this will force these specific n equals 0 tensor structures. So now I've simplified things, and so now I can write down the cross-channel books. So for that, I'll just need a bit of notation. So these epsilons are bookkeeping parameters for the light cone limits I drew. Now, I'm going to define, I've already imposed the twists here in step 0. And I define the following parameters. Alpha 1 is HO, alpha 2 is 2H5, alpha 3 is HO. And at leading order, my operators take this very simple form. The leading divergence is 1 over epsilon 1x epsilon I. I get this first order differential operator times and then I'll get these subleading corrections, which I won't look at in this example. And once again, we can go through the remaining steps. So once again, I'll act with this operator on my subleading order in the left-hand side. This will tell me that it's order 1 over epsilon 1/6 epsilon I. So that means the cross-channel sum must be the dominant part of the cross-channel sum is the regime where GI goes like 1 over epsilon 1/6 epsilon I. Step 2, I diagonalize these guys simultaneously, but as you can see, it's quite simple to do. They all have the same commuting operator of order 1 here, and then these are first order operators that you can diagonalize as well. So I'll get this kind of simple, these simple power laws and exponentials. I guess it's just GOI n equals 0. So I get normalization, this exponential, so it was the OP limit boundary condition that allowed me to identify this as the MST spin. And you can see that consistency with this scaling forces the MST spin to go like 1 over the light distance of, well, the distance of x1 and x6. Okay? And so this is all I need to bootstrap these OPE coefficients in this specific scaling limit. Okay? And that's essentially all the work is done. I can write down the simplified crossing equation at this order. And it'll be something like a density contribution, which, as I said, I've already solved for, plus C phi phi O squared, the 4-point function, and the 4-point block, times this beta function of h bar, using the twist over 2, the twist in the cross channel that I've already identified, u6 to the minus 2h5, and then finally the log coming from the leading order in the light cone limit of the 4-point block. This will be equal to the sum over blocks in this, of these blocks in this regime. These are the OP coefficients I solved for. And then, of course, the books. Okay. So I hope it's clear enough that this can be easily solved now. Essentially, we just put in the usual power law ansatz. It'll be set Pj kappa and J kappa equals product times kappa to gamma times a constant. Okay, and you can solve for this. And you'll obtain this log times power law asymptotics in U6 and U2 respectively. And so, okay, I could write these down explicitly. As I said, this is from the OP limit boundary condition that we obtained it. I sketched how we did this in the 5-point. It's a very similar derivation in this case. And yeah, so we can get these OP coefficients of several double trace operators in this very unexplored regime of large MST spin.
Do you have like an intuition of the structure of this middle operator? Since you are making J and K large, but O is an operator of finite spin, what type of structure of derivatives do you have such that J and K are both large at the same time? Because there's just two operators and one of them has a few indices, so how can you make two long rows that are antisymmetric with respect to each other? I don't really see.
Well, it's the usual story, right? You just, I mean,
it's not the usual story because there are two rows now, so you need to antisymmetrize. And how do we just derivatives and I don't know? Suppose O is the stress tensor. They're just two spin indices. What's the structure of the operator? Because you cannot antisymmetrize derivatives.
Well, we went over this, I think. Yeah, that's a good point. I don't think there's any. So the question is there a group theory result that bounds the second row of the Young diagram in the tensor product of two representations with one row, and one of the rows is fixed?
Yeah.
I'm not aware of such a group theory results.
I'm just asking physically if you can build like phi T mu that write some derivatives in the middle and cook up something that looks.
Yeah, so I think it can be cooked up. I'm pretty sure I did this exercise just on a piece of paper. Because at the end of the day, it doesn't quite matter where the initial STT spins come from. As long as you have a source, which are all your derivatives, you can just anti-symmetrize it. I'm not sure I can write this up. I'm not sure I have a simple example to cook up, but I think it works.
Okay.
Of course, yeah. Maybe this is a good place to transition to the outlook.
So the final block for the column is this box 2?
Yeah. In this regime. And there's for example, lots of subtleties, one of which is this operator, D2, the middle leg Casimir. If it wasn't the log contribution that I took, but the subleading contribution, which is order D2 to the 0, this would not have been Casimir singular. So I would have acted on the left-hand side, I would have gotten 0 at this order. And so only the subleading part that scales like only with x16 would have been non-vanishing. So I would have had to, so if I want to consider the contributions of these guys, I'm going to have to sum over more complicated blocks that scale in a less severe way with my light limits. And this is actually what we observe if we want to compute things like triple twists of the coefficients. So this makes the job harder, but can still be done, and particularly at the level of asymptotics, not normalization, it's very easy. It continues to be very straightforward to go through the three-step process. So maybe I'll finish with the outlook. So what we're interested in. So first of all, the full generalization of this example, the identity OO, and we'll want here phi, phi O, phi, and if I don't make these simplifying kinematics with x1 and x2 as I did in my example, I'll have in all generality a triple scaling regime where these three numbers go to infinity, but then these ratios by construction are finite, and I have 2 degrees of freedom left that I can tune. I took the particular case where I put the n's to 0, but one can look more generally, and so we deduce the OP coefficients of this setup. Yes, the next interesting example, as I mentioned, was getting triple twists here. That's kind of what's most interesting. But you see that if you want to take a crossing equation that's planar, cyclic symmetry, there's not many ways to make these triple twists appear. It turns out you have to take a sum over double twists in the direct channel. But if we put the identity in the exchange, this is a sum over 4-point functions. We know how to do this. And once again, you take step 0, and you'll see that you have to get triple twist. The one thing is the novelty here is that J2 will have subleading scaling. It'll scale like epsilon 1/6, and that leads to more complicated equations to solve for blocks. Actually, let me put it this way, the equations for blocks are actually still very simple to solve. What becomes more difficult is getting the normalization. So essentially, we're still, so the full OP coefficients still work in progress. The asymptotics in J, we have these simple arguments, the normalization, work in progress. Let me also mention that if you wanted to have this from the start, you can easily see that at the level of your 4-point function is equivalent to identity exchange in a non-planar setting just by crossing the 4-point function. Okay, and so the last comment I'll make before wrapping up is the most important thing to compute, anomalous dimensions. And so kinematically we know that we can get anomalous dimensions this way. So for O prime being either double twist or single twist, and O being a leading twist in the phi OPE, we know that in our cone we'll get maybe let me call it Otilda to make it clear. We expect that in this setup, due to the kinematics, we'll obtain anomalous dimensions of the operators at the middle leg, so of these phi Otildas. In progress. It'll generally be at order 1 over maybe I can say J2 Okay, this is our goal in the near future, and as I said, this result will soon appear, and this is work in progress. Thank you.
Jeremy, so here it's even asking the question is extremely subtle. So the number of degenerate triple twists is infinite with spin. There's an infinite degeneracy. So are we computing some infinite average? So does this constrain like the scaling of things?
Yes. Yes. So that's indeed. We're going to be computing averages, and you can already see this here. Indeed, I hope this wasn't too misleading. Right, because in this case what we find is because the J has subleading scaling, it'll scale in the same way as kappa and n. And because they'll scale in the same way, there will not be will not be able to kill the sum. I'm trying to think of a clear way to say it. In other words, because this is subleading, the cross channel, so the direct channel asymptotics will not be sufficiently constraining to turn all finite sums into integrals with fixed power law asymptotics, but we'll continue to get some finite sums in this space. Yes. So indeed, and this fits. So I had some interesting discussions this week, and seems to fit with the intuition that the bootstrap for multi-trace operators is likely to give you constraints in the form of sum rules, averages on data. So, but what's really very solid with this method, and what you can see very easily, is, as you said, the universal asymptotics of these OP coefficients in the STT spin J. That's a very solid result.
More questions? If not, let's thank Jeremy and Lorenzo.